Dear students, in the previous class we have discussed how to make inferences about two population means using independent samples, assuming that the population standard deviation of these independent samples are equal. Now, in the previous class, we have just described the Z test procedure and suggested that as population standard deviation is unknown, Z test procedure will not work. So in this class, we develop a workable procedure to make inferences about two population means, assuming that population variances or population standard deviations are identical. The first step in the procedure is to develop a test statistics. As we have discussed in the previous classes, without developing a test statistics, we cannot make inferences about population parameters. So we first develop a test statistics. We assume that the variables under consideration, the variable under consideration from both the populations are normally distributed. So for example, the salary of college professors, salary is the variable which is assumed to be normally distributed, whether it is from the professors of private universities or professors of public universities. To develop, we also assume that population standard deviations are same. That is, the standard deviation of the population of salaries from the public and private universities are assumed to be same. Now we denote, let us denote sigma. Denote sigma as the common standard deviation. Common standard deviation of both the populations. Then, for independent samples, the distribution of the sample statistics x bar 1 minus x bar 2 for independent samples, the standard version of the random variable x bar 1 minus x bar 2 is, as we have described earlier, is equal to x bar 1 minus x bar 2 minus mu 1 minus mu 2 divided by sigma of, and it was assumed, so if sigma of sigma square 1 by n1 plus sigma square 2 by n2. This is the standardized version of the sampling distribution x bar 1 minus x bar 2. When we compare the mean of two populations, the sampling distribution is x bar 1 minus x bar 2 and its standardized version is this. And if we replace this sigma 1 and sigma 2 with the common sigma, then Z is equal to x bar 1 minus x bar 2 minus mu 1 minus mu 2 all divided by sigma. We have used the notation sigma into 1 by n1 plus 1 by n2. This common sigma replaces sigma 1 square and sigma 2 square. So, and it is taken out. We have sigma into root of 1 by n1 plus 1 by n2. And this we have used the notation sigma p, pooled, because it is assumed that the standard deviation of both the populations are same. But the problem is we cannot use this test statistics. We cannot simply p, as we are dealing with population. We cannot use this test statistics due to the simple reason that sigma is unknown. And as population standard deviation is unknown, we have to replace it with the sample information to estimate the unknown population standard deviation sigma. So, what we do here is we replace the unknown population standard deviation with its sample counterpart, sample standard deviation. So, what we do is, as sigma square is, sigma 1 square is estimated by S1 square, sigma 2 square is estimated by S2 square. That is population variance of the first population is estimated by its sample variance S1 square, population variance of the second population by its sample variance S2 square. And these are the estimates of sigma square. And what we do is we use S1 square for sigma square 1 and S2 square for sigma square 2. And these are taken as estimates of sigma square, because we assume that sigma 1 square is same as sigma 2 square. Population standard deviations or population variances are assumed equal. So, after estimating this, that is by using S1 square and S2 square as estimates of sigma square, or S1 and S2 as estimates of sigma, we pool these estimates by weighting them according to the sample size. We pool these estimates by weighting them according to the sample size, or what is known as degrees of freedom. Not with the sample size, but with the degrees of freedom. So, the estimate of sigma square is, S square p pooled n1 minus 1 into S1 square plus n2 minus 1 into S2 square by n1 plus n2 minus 2, and its estimate of sigma is Sp is equal to root of n1 minus 1 into S1 square plus n2 minus 1 into S2 square by n1 plus n2 minus 2, where p means pooled and Sp is pooled standard deviation. Pooled standard deviation. So, what we do is, in this formula of Z, sigma is replaced by its sample estimate SP, so that you will get x bar 1 minus x bar 2 minus mu 1 minus mu 2 divided by SP into root of 1 by n1 plus 1 by n2. Sigma is replaced by SP, and this is the required statistics. Because in this statistics, all the quantities are known to us. All the quantities are known to us. So this is the required statistics for comparing two means when sigma is unknown but assumed to be equal. Now let us give a formal definition. Suppose that x is a normally distributed random variable. X is a normally distributed random variable on each of the populations with the same standard deviation. X is a normally distributed random variable such as salary on each of the populations with the equal standard deviation. Then for independent samples of size n1 and n2 from this population, the variable x bar 1 minus x bar 2 minus mu 1 minus mu 2 divided by SP into root of 1 by n plus 1 plus 1 by n2 follows T distribution. This quantity has T distribution with the n1 plus n2 minus 2 degrees of freedom. We lose 2 degrees of freedom because we have to estimate two quantities from the sample, x bar 1 and x bar 2, and total sample size is n1 plus n2. So the test statistics used for testing the hypothesis that the population means are same is given by this quantity, and under the null hypothesis that H0 mu 1 is equal to mu 2, this T becomes equal to x bar 1 minus x bar 2 divided by SP into root of 1 by n1 plus 1 by n2. The reason is, if H0 is mu 1 is equal to mu 2, it follows that mu 1 minus mu 2 is equal to 0. So this quantity follows T distribution with the n1 plus n2 minus 2 degrees of freedom. So we call this testing procedure as pooled t-test procedure. So the testing procedure used to test the hypothesis, if we assume that the population variances are equal, is known as the pooled t-test procedure. Now let me introduce the pooled t-test procedure formally. Remember that it is based on 4 assumptions. The assumptions are simple random sample, independent samples, normal population or large population, and equal standard deviations. Equal standard deviations. These are the assumptions. Normal populations, large populations, independent samples, equal standard deviations. Then what are the steps? First is formulation of hypothesis. Mu 1 is equal to mu 2. H1, mu 1 not equal to mu 2, mu 1 greater than mu 2, mu 1 less than mu 2, depending on the problem at hand We have a two-tailed test. We have a right-tailed test and we have a left-tailed test. Depending on the alternative hypothesis, we can have the three types of H1. That is the first step. The second step is to determine alpha, say at 5% level or 1%, 10%, whatever it is. The third step is to compute what is known as the third step is compute T, where T is equal to x bar 1 minus x bar 2 by SP into root of 1 by n1 plus 1 by n2. And as we have just suggested, SP is equal to root of n1 minus 1 into s1 square by plus n1 minus plus n2 minus 1 into s2 square by n1 plus n2 minus 1. SP is calculated by the formula. And all these quantities are known because SP can be calculated. If sample variances are known, sample size is known. And the third step is find the critical values. Fourth step is find the critical values plus or minus T alpha by 2 minus T alpha and T alpha. If you have a two-tailed test and alpha 5% minus T alpha by 2, 2.5%, 2.5%. If you have a left-tailed test, then minus T alpha 5%. If you have a right-tailed test like this, T alpha 5%. Then obtain the value of the test statistics from the sample using this formula and compare it with the critical T values. If the value of the test statistics obtained is in the critical region, reject H0, otherwise do not reject H0. Or you simply report the P values, and if P is less than or equal to alpha, again the conclusion is same conclusion. Now regarding the pooled T test, consider these points, remember these points. One is regarding assumptions 1 and 2, remember this simple random sample and independent samples. This test procedure is highly suitable for designed experiments. Where simple random sampling and independent sampling is applicable. And regarding normality, pooled T test is robust to moderate violations of normality. But remember this, if outliers are present, even for large samples, the procedure will be affected because sample mean and sample standard deviation, as we have studied, are not resistant to outliers. If outliers are not present, this is robust to moderate violations of normality. So one must check for outliers using box plot as an example. Normality can be tested by using what is known as normal probability plot. And pooled t-test is also robust to moderate violations to equal standard deviations. Now the question is, can we test for equal standard deviations? An F-test procedure is available for comparing two standard deviations. That is a topic which we will see later. But this is not generally recommended because F-test is not at all robust. So, as a rule of thumb procedure, if the ratio of, you calculate the standard deviation of sample 1 and sample 2, and if it calculates the ratio large by small. If it is less than 2, then we can assume that the standard deviations are same. Standard deviations are same. Now, this is the pooled t-test procedure. Let me consider an example to clarify what we have studied. And in the example of private and public universities, X bar 1, this is for private, public. This X bar 1 is 98.19, S1 is 26.21, N1 is equal to 35. X bar 2 is 83.18, S2 is equal to 23.95, N2 is equal to 30. Now as you can see, there is not much difference between the standard deviations. So our null hypothesis H0 mu1 is equal to mu2 tested against mu1 not equal to mu2. Now applying the t-test procedure, you will get the value of t as 2.395. That is the empirical t value obtained from the sample. We will do this using the softwares. That is why I am not applying the formulas. And if alpha is 5%, and we know that the degrees of freedom is 35 plus 30 minus 2 is equal to 63. For 63 degrees of freedom, the T alpha by 2, two-tailed test is 1.998. So as you can see, and the p-value is 0.0196. As you can see, p-value is less than 0.5, or the empirical t is less than the critical t. So null hypothesis is rejected. We conclude that the mean salary of private coli posers is different from public coli posers. We can change the alternative hypothesis as mu1 greater than mu2 if you suspect that private coli posers are getting more than public, or mu1 is less than mu2. That is the choice of the researcher. So in this case, H0 is rejected. Now, as we have discussed earlier, we can use the confidence interval procedure for the difference between two mean values. We can construct the confidence interval for testing the difference between two values, and the procedure is known as pooled t interval procedure. The procedure is known as pooled t interval procedure. Let us see how we do it. Now, for confidence interval of 1 minus alpha, find t alpha by 2 with the degrees of freedom is equal to n1 plus n2 minus 2. Then the end points for the confidence interval mu1 minus mu2 is equal to x bar 1 minus x bar 2 plus or minus T alpha by 2 Sp into 1 by n1 plus 1 by n2 as usual. And in our case, alpha is 5%, degrees of freedom is 63, and T alpha by 2 is equal to 1.998, and applying this formula you will get a 2.49 to 27.53, the 95% confidence interval for mu1 minus mu2. And the interpretation is mean salary of private colli professors exceeds the mean salary of public colli professors somewhere between 2,490 to 27,530. Remember the interpretation of confidence interval for comparing two population means. So, and the procedure we have discussed is test of significance approach. If you want the confidence interval approach, you construct the 95% confidence interval and see whether 0 is included in the interval or not, because the null hypothesis is mu1 minus mu2 is equal to 0. As 0 is not included in this interval, again null hypothesis is rejected. So this procedure is known as two sample